Suppose I have some distribution of values that I'm going to call x. This is going to be the population distribution of x. And it doesn't have to be normal. It has some particular shape, but it is centered at a mean that I'm going to call mu x, and the variance of x is some known quantity that I'm going to call sigma squared x. And suppose I have some other distribution of values that are y. So maybe these are the heights in one population, the heights in a different population. Perhaps I'm interested in the heights of women who are black versus white, something like that. I have a certain population mean. Those values have some mean. Whether I know what it is or not, there is some mean in that population. And these values in the population have some variance. And suppose that I know what it is. Okay? By the central limit theorem, for each of these two distributions separately, I can say that x bar should follow a normal distribution. Even though this curve wasn't normal, x bar should be normal because of the central limit theorem. X bar should follow a normal distribution centered at mu x with variance sigma squared x divided by whatever the sample size was, which I'm going to notate nx to make sure we're thinking of x. In parallel, I can say that y bar, by the central limit theorem, is expected to follow a normal distribution centered at mu y with variance sigma squared y divided by n y. Okay? So all I did here was apply the central limit theorem. What else can we say? Well, it turns out that the difference in two normals is also going to be normal. So if I take x bar minus y bar, in other words, I take the sample mean that I obtain from one data set and the sample mean that I obtain from the other data set, and I take the difference, that quantity, that difference, is expected to follow a normal distribution. What do we expect the mean to be? What do we expect on average, the difference in the average of a few black women's heights and the average of a few white women's heights to be? Well, on average, it would be equal to whatever the actual difference in population heights is. What is the variance of this quantity? What is the variance of x bar minus y bar? It certainly has to incorporate this quantity and this quantity, the separate variances of x bar and y bar. So there's a couple key things here. One key idea is that x bar and y bar are independent. The fact that I sample certain people from this group has nothing to do with whether any particular individual is included in my sample for this group. I have independence. So that means I don't have to take into account any correlation between x bar and y bar because that correlation is equal to 0. What else? When you subtract two quantities that are random, so these are both sample means, and they're random because we could have many different samples from the population. When you subtract two quantities that have variance, the overall variance should increase, right? If I take a quantity that has uncertainty and another quantity that has uncertainty and subtract those two, overall the new quantity will have even more uncertainty because there's two different quantities that had uncertainty. Okay? So it turns out that the variance of x bar minus y bar is equal to the sum of the two original variances. The reason it's the sum and not the difference intuitively is that if I take a quantity with uncertainty and another quantity with uncertainty and subtract, overall I should have more uncertainty. And the other thing to know is the reason I can just add these and not have some other term here is because I'm assuming independence. I'm assuming these are not correlated. So now we could exactly do a z-test. If we wanted, we could set our null hypothesis and directly use x bar minus y bar as our test statistic. So our null hypothesis typically is that mu x is equal to mu y, that the two populations have the same mean. Typically, we're looking to see whether our data contradicts the possibility that the two groups have the same population mean. That is the same thing as saying that the difference in population means is equal to 0. Note that we could do all the same things here if we filled in some number other than 0. Perhaps I want to do a hypothesis test for the null hypothesis that the difference between heights in these two populations is 2 inches. I could do that by putting a number other than 0 here. But the typical number to use is 0 because usually that's what we're interested in. So then for a test statistic, If I wanted to, I could just use x bar minus y bar because I have a reference distribution for that. Under my null hypothesis, mu x minus mu y is equal to 0. And if I say that I know sigma squared x and sigma squared y, and I do know nx and ny, I exactly have a reference distribution, and this will work fine. However, just like in the case with only one sample, conventionally we use as a test statistic this difference in means minus the null hypothesized value divided by the square root of the variance. Why do we do that? The reason we do that is because then we get to use as our reference distribution the standard normal, which is centered at 0 and has values between -2 and 2 with probability 0.95. This is a two-sample z-test. It's a two-sample z-test. What does it assume? It did not assume normality of the populations, but it did assume that we know the two variances. It assumed independent sampling, and it assumed that the sample sizes were big enough that the central limit theorem kicked in. The central limit theorem is a good enough assumption here.